Okay, here's the second half of the chapter on work done, chapter 17, and we're really going to move into the useful side of it. So last lesson was very much about the concept of what we mean by energy and so on. We're going to use how we can then calculate that and the ultimate law in the universe about what happens to energy as the basis for all calculations. So first things first, we'll come up to the key idea, which is it's still all about that equation. Now you will need to be able to derive a couple of equations from this. One of them is pretty obvious, the second one a bit less obvious, but most of it is about how we use it to calculate things. And the crucial idea is, of course, that it just changes type, so the amount is always the same. So we need to think about how well that energy is used to do what we want it to do, and this is our idea of efficiency. So the first bit is the key idea of what efficiency is, which is that it's all about doing work, okay, but doing work increases or reduces depending what you're doing. The internal energy store, or the energy store, let's just call it that, okay, or energy stored, okay, that's the key concept, but it's also the fact that it's got an and in there. So and energy, and I'm going to be very vague here, lost or dissipated to the surroundings. Now if you excuse me, spell that right, if you listen to popular podcasts and things, this is called heat death. Everything eventually ends up as thermal energy elsewhere, but in smaller and smaller and smaller amounts. Okay, it's the final law of thermodynamics. So we're going to use that idea. Okay, we know that it's changed, but the fact that it gets into smaller amounts, it increases the entropy of the universe, is a big thing. Now at GCSE, hopefully you used this this diagram, Sankey diagrams. It's a nice idea. It's just very visual to see how well something is at doing its job. The work done is the process. Okay, so here's our work arrows. And not all of it is done usefully. Okay, so by convention with Sankey diagrams, the energy that goes forward to the final job is what you want it for. Most of it is fairly typically like this. Most of it will be lost. It'll be wasted somewhere to the surroundings, okay, in forms that you are not after, in forms that you do not want. So more importantly, how do we work it out? Well, it's all about this this symbol nu, okay, which is efficiency. Okay, often used to put in efficiency. Now it's not in our data sheet, this, it's basically the concept. So it's how much of the total comes out as useful. Okay, so think of it as terms of energy transfer, if you prefer, or how much work done, because of course that's what's transferring it. And it's how much ends up in a form that you want. So useful energy at the end as a fraction of how much you started with. So this in at A level is always a fraction. It'll always be less than 1. So 0.9, 0.6, more frequently about 0.3 or 0.2. So depending what the device is, it can be really low. More usefully, we're often expressing it in terms of power, because power is how quickly it's done. So down at the bottom of the sheet, let me just move that on there a bit easier. What we can do is express it in terms of power. So let's do this in a better way, a more useful way, which is you're usually after the useful power. Okay, and we're going to take that across, so we're multiplying those. So that's our efficiency multiplied by your input or total that you've got at the beginning. Okay, so power transferred. Okay, so that's our normal thing. some fraction of the power transfer comes out as what you want as a useful process. Okay, so it doesn't need to be any more complicated than that. Keep it simple. It really does make it a lot easier to kind of do the ideas about it. But the crucial point is we'll often talk about percentages. You just need to think of that as a number out of 100 to turn into percent. So if it's 0.9, that's 90%. Okay, so it doesn't need to be genius. But calculation, that's a fraction. So what fraction? Not percentage. Okay, so as I said there, much easier to do it as a ratio. Now if we use that, then we can put it into things that are useful, and usually for a lot of our calculations it's going to start with the idea of something high up. So gravitational potential energy, GP, gravitational energy store. Doesn't really matter what you want to call it. GP is still used even though we've changed our ideas of energy. Let's just move that out of the way. So if we were to think about that, it's quite easy to work out what's going on. So if we are not going to accelerate it, because that has an effect on things, if we just lift something up nice and steadily, quickly or slowly, but nice and steadily, then what we'll find is that we'll be using a constant force to do it. Okay, so constant lifting force. Okay, therefore, so that symbol, if you've not seen that before, 3 dots, therefore you have a constant lifting force. And so because of that, what you end up with is the amount of work done is, from our equation, force times displacement. Now we're lifting it vertically, or more importantly, we want it to gain vertical height, so actually that's what matters. Why? Because the force is vertically upwards. Okay, if you're moving it as a slope, you're still basically trying to get it uphill, because gravity will act down. The effect of gravity is downwards, and therefore you need to think of it in terms of that. Now if we break that up, we'll use the simple version of Newton's second law. mass times acceleration. I'm going to multiply it by s. Well, if we're thinking of the vertical and we're thinking of the acceleration downwards, therefore how hard you have to push, because they will be equal. Okay, so constant lifting force, we'll come back to that. If it's a steady lift, then this will equal weight. We'll come back to debate that when we do dynamics, because I'm sure that will have a few people pondering. But if we look at that, we're basically just saying that the work done can be thought of as m, acceleration due to gravity, times by the vertical displacement h, and that is how you get your potential, or gravitational. I tend to call it grav, just make it easier. Okay, so that is how you get your gravitational equation. Simple. Force times by the vertical distance. In reverse, this can turn back to because of the force due to gravity. If it moves it down, then that work done by the gravitational field rather than you lifting it up will be the same amount. So that can convert into something more useful, and we use that and have been using that for a few hundred years. Falling water, for example. Now, if we think about the kinetic energy, ever so slightly harder, because it is about due to that kind of inertia that it has. So it's all to do with its motion and obviously the object. So it's not about force. It could be horizontal kinetic energy, it could be at a slope, it could be whatever. So the key is, this is about change, how much you have given it. So what we need to do for this one is you need to think of it in a kind of a broader start. So I'm going to bring in the idea, if it's at rest, then we know from Suvat that's 0. We're going to use Suvat to help us out here. Okay, so imagine it's a petrol car. Okay, so better put that, if petrol, or if fuel let's say stick with petrol because it's shorter. So fossil fuel type thing. Then what you have is your chemical energy store will change because something is pushing, and that something is pistons. Okay, so as you release that, it gets hot, you ignite the fuel and so on. Pistons do work. And so that's what transfers your energy into that kinetic energy store. Okay, into that different type of useful energy. So how much work do they do? Well, in the end, it's all about the force needed to keep the car moving, which is what we hinted at with the power equation. However, think of it in basic terms. If we take the same starting place, so we think about the work done, okay, then we have force times displacement forward, so not the pistons but the overall for the car, which again makes the car accelerate from 0 by a certain amount to gain a certain amount of kinetic energy. And then multiplied by the displacement it goes. Now, if we think about acceleration, as long as it is a nice constant acceleration, then we can use Suvat. Okay. Now, if we think of the equation 2as equals v squared minus u squared, or v squared equals u squared plus 2as, it doesn't really matter. You can see that we could substitute that straight in and just need to divide this side by half. So that's going to equal half of m v squared minus u squared. And I think fairly obviously, because you did this equation at GCSE, you can see that if we start from 0, then this simplifies. So as u equals 0, then what we've got is the work done accelerating our car up to that speed will equal to the change in, and I'm going to put change in mv, half mv squared, okay, which is of course kinetic. Okay, so again, just using basics, we can derive the equation from this, and it all depends on that change in energy. Okay, so again, we've got a change in energy here. I should say I made a mistake because I haven't actually said how much the height has changed. It's not about the height, it's how much you change the height. So mg delta h. So those are a lot of the key questions, those moving back and forth between things going downhill, things going uphill. And if you look on PHET, then you've got Energy Skate Park. Again, really good example of that, and the effect of losing energy to surroundings. So you can add in friction, or you can take it away to make it perfect. You can do it under different gravitational conditions, etc., etc. So great little thing to experiment with just to get your head around it. But the key bit, there's other types. Okay, so don't forget we've already done this methodology earlier on in the year. Okay, so you know this one, using that same idea, so just remind you we did the proof at the time, but S varies with force in a stretched with force applied to the stretched system. Trying to say that in English. F is proportional to X is the one we've used. Okay, so I'm going to just put that in speech marks there. So if working with the idea that we are displacing the thing at the bottom of the spring or at the end of the spring, then what we have to use is we have to think about that average. So must use, you don't have to, you could differentiate it as well, but let's keep it simple. Must use average force. Okay, excuse me, can't spell force, which is of course maximum subtract 0, which is the minimum, divided by 2. Okay, so if we put that into it, then again work equals Fs. We're not accelerating anything this time, it's about that stretching force, so we could just put in F half F, because that's the average of that. If you want to think of it as max, or you could go up to that point, you could make it more general, times by x, where x is the extension at that point, and that equals your strain. Okay, so they are all types of energy, E subscript strain, or if you prefer, E kin, E gravity, and others. So you can change them all. They are all types of energy that work back and forth. Okay, but the crucial bit, as I said, right in the original part of the chapter in the lesson, is actually what is it that's doing the work? What is the force involved? Okay, so here's some examples. Here's some common kind of examples, things going down slopes. Well, it's the weight usually, or a component of the weight pulling it down that slope or making it drop. Okay, so it's that that's making it happen. However, whether it's just spotted, whether it's perfect or not, prefect, if it's perfect or not, you're still going to have that same loss in original energy store. Okay, so if you're halfway down a ramp, you will have half the GPE. Might not have all turned into kinetic energy, you might have turned into other stores as well, but you will have lost half the original amount because it's to do with height. Pendulums as well, and swings, these are really good because they're always changing direction, so you can't really do it very easily with any other system. We do have a look at it in terms of forces next year, but it's pretty tricky, or fairly tricky. So it's much easier to just think about how much has gone up and down, because that's a far better way of calculating it. Bouncing balls as well, same kind of thing. So again, you're reducing the amount of kinetic energy as it goes up, but it's gaining potential energy, okay, that gravitational energy. But each one, again, we're always losing energy because there's always an additional force, and that's the bit that matters. So there's always work done against resistive forces. So the truest way of talking about this, if we're looking at going up and down, which is our most common kind of questions, what we've got is our change, notice that, change in gravitational energy will always be our starting place, but it's going to equal the change in kinetic. Okay, so loss in that will be a gain in this. You could say they add up to 0, but of course they don't quite add up to 0 because there's always plus this lost dissipated energy. Okay, and that is because of work done against resistive forces. Okay, e.g. drag. I'll put that in because it's such a common one. Okay, so if you've got air resistance, you're doing work against resistive forces, and that is what's causing your inefficiency. It's always something to do with work done, resistive forces. They are doing the work. Force in the wrong direction. And that is all there is to it. Energy is a really straightforward idea. Trying to explain what it is probably the hardest thing. So keep sticking with those stores. But if you think about what we've just done there, it leads us into the hardest question. So you've got your three types. You've derived where they come from. We know they're all equal in change. If one increases, the other one will go down. We go back to that very first part of the chapter where it's our work done is moving that energy into different stores, 2, 3, maybe 4. You know, you can have lots and lots of arrows peeling off the side, showing the lost energy, the work done against resistive forces. But in the end, they all come back to that simple law of thermodynamics. Energy in equals energy out plus work done. Okay, so that store turns into another store plus work done against, okay, reducing it. So when you get into the questions, there are some more straightforward ones, okay, but in terms of looking at questions 10 and 11 and 12, it's just thinking about what happens when you're changing variables and how that swaps. So here, for example, we're going down a hill, the work is done, the useful work is done, transferring into kinetic energy, ignoring any air resistance on the way down. It's then transferred into another energy store, and that's your resistive force. So all your energy will go into that if you crash into a cushion.